It's Alexandria in roughly 300 BC. A man named Euclid is writing a book known as The Elements. The book is composed of 13 volumes and outlines the foundations of geometry. It lays the groundwork for essentially all of modern mathematics. It's the most successful textbook of all time, and it's been republished more times than any other book in history, second only to the Bible. So yeah, it's kind of important. In The Elements, Euclid outlines 5 postulates, or axioms. These are statements that are taken to be true without the need for proof. It's basically a starting point from which other proofs or judgments can be built from. Euclid's postulates are as follows. 1. You can draw a straight line that connects any 2 points. Makes sense. 2. Any straight line can be extended out to infinity. 3. Given any straight line, you can make a circle with the line as the radius and one end as the center. 4. All right angles are congruent. And finally, 5. If a straight line falling on 2 straight lines makes the interior angles on the same side less than 2 right angles, the 2 straight lines, if produced indefinitely, meet on that side on which the angles are less than the 2 right angles. So obviously, one of these things is not like the other. This final postulate became infamous. To many, it seems that Euclid himself only used it when he absolutely had to, proving every other thing he possibly could using the first 4, and then finally bringing up the last one when he just couldn't anymore. In the many centuries that followed, mathematicians would struggle to derive it from the other axioms, and the parallel postulate would become one of math's largest mysteries. But what does this postulate actually say? Essentially, given a line and a point that's not on that line, you can make one and only one line that doesn't intersect with the other line. You can only make one parallel line because any tilt, no matter how slight, will eventually result in the lines meeting on one side. When written this way, it might seem like common sense, but in reality, it took hundreds of years for the parallel postulate to finally reach its conclusion. One of the earliest attempts at dealing with this was by another ancient thinker known as Proclus. This guy dismissed all of the incorrect proofs before him and proposed a new one of his own. Take a line, we'll call it C1, and draw another line, C2, parallel to it through a point we'll call A. Now take another point, B, and draw a line C3 through it. From there, draw a line perpendicular to C2 that meets point B. Since the further along we go on C3, the longer the distance of this perpendicular line gets, and the distance between C1 and C2 stays constant, then at some point there has to be an intersection between C1 and C3. He was wrong too. It relies on information outside of the first 4 axioms. It assumes that the distance between parallel lines stays the same. This assumption isn't included in any of the other axioms, and it can't be derived from them either. This trend continues throughout history. For example, hundreds of years later, another mathematician by the name of Ibn al-Haytham, who's known for many other scientific discoveries, used the same assumption in his own proof, which states that the path traced by a perpendicular line moving across another fixed line will draw another line parallel to the fixed. Hundreds of years later, in the 11th century, a Persian mathematician by the name of Ghiyath ad-Din Abu Futuh Umar ibn Ibrahim ibn Salih al-Khayyam al-Naisaburi, or just Omar Khayyam, had begun to sow the seeds of a revolution in geometry. Khayyam took issues with the ways that mathematicians before him had approached the problem of the 5th postulate, such as Ibn al-Haytham's use of motion and transformation, and he endeavored to do better. Khayyam believed that all his predecessors' proofs were all even more complex than the postulate itself, and instead believed that new propositions would need to be supplemented to Euclid's original works. Among these propositions was one about this quadrilateral. He considered 3 cases for the angles at the top. Either they were right, or they were obtuse, or they were acute. He threw away the 2 latter cases because they were obviously contradictory. You can't have a rectangle whose angles add up to more or less than 360 degrees. Eventually, Khayyam's work was commented on by another mathematician by the name of Nasir al-Din al-Tusi. His work eventually reached England and translated by John Wallis. Wallis's work was then studied by the Italian mathematician Girolamo Saccheri, who again brought up the quadrilateral from Omar Khayyam. Saccheri came to the same conclusion as Khayyam, that the 2 top angles would have to be right angles, or contradictions would arise. Finally, in the 19th century, Nikolai Lobachevsky, this guy whose name I can't pronounce, and Carl Friedrich Gauss all asked the same question and came to the same conclusion separately. What if there are cases in which those summit angles aren't right? What if there are geometries that are different from Euclid's? So what the hell am I talking about exactly? I'll explain with a more visual approach. This entire time we've been talking about Euclidean geometry. Geometry performed on a flat plane like a piece of paper. But the kinds of planes that Lobachevsky and the others thought about were different, because those planes were curved. Take the surface of the Earth. A straight line on this spherical plane is known as a great circle. It looks like this. It always passes through the center of the Earth, and it always bisects the Earth, meaning it cuts it in half. The path of a great circle is always the shortest distance between two places on the surface of the Earth. Have you ever been on a flight and looked at the flight path on the screen in front of you and wondered why it was curved? It's because that's the shortest possible distance to travel from point A to point B on the surface of the Earth. Curves representing the shortest distance are also known as geodesics. So, a reasonable question would be, what do parallel lines look like on a spherical surface? They don't exist whatsoever. Look at the lines of latitude. These are all great circles, and they all intersect with each other at the north and south poles. You can't form a great circle that doesn't intersect with another one. But that's just one non-Euclidean geometry. There are more, in fact. There's another one known as hyperbolic geometry. In hyperbolic geometry, there isn't just one parallel line from another, but an infinite amount of parallel lines from another. We can represent a hyperbolic space in a shape that looks kind of like this. These circle segments represent straight lines, and so does this central one. As you can see, we can draw this curve that never intersects, and this one, and this one. You can draw infinitely many. And just like that, 2,000 years of geometry had been completely upended. A perfectly reasonable person would look at all these absurdities and ask the all too common question when it comes to math. Who the hell cares? What in the name of God am I going to need hyperbolic geometry for? Well, recall one of the founders of non-Euclidean geometry, Gauss. You might know him for doing, any of this. One of Gauss's students was a man named Bernard Riemann. You might recognize Riemann by the literal $1 million question that bears his name, but that's not what we care about today. Riemann produced what we now call Riemannian geometry. It was revolutionary in its own right, but it laid the groundwork for one of the most important scientific discoveries in human history. Up until the 19th century, scientists thought that light moved through a medium known as the ether. This magical ether was a substance that filled the entire universe and was completely invisible and undetectable. Except for the fact that it had to exist so that light could pass through it, of course. The problem was, properties had to keep being added onto the ether for it to exist, and they just contradicted each other, and it was a complete mess. But eventually, this idea was thrown away in the paper on the electrodynamics of moving bodies. You know when that name shows up, that shit's about to go down. In just a few pages, Einstein goes on to change everything about light, motion, and time. The theory would be known as special relativity, and a few years later, he did it again, but this time, it was general relativity. Einstein posited that the force of gravity wasn't a result of the mass of objects pulling on each other, but in fact, the force of gravity wasn't a force at all. It was the curvature of space-time. Imagine you and your friend are standing next to each other on the surface of the Earth. You both walk in what looks to you like parallel lines, the lines of latitude. But eventually, you would meet at the poles. This is kind of the same phenomenon going on. Objects always naturally move in a straight line. It's just that the space around them is curved due to massive objects. The fabric of reality itself isn't Euclidean at all. And what language was all this written in? Well, it was written in German, but more accurately, it was written in the language of mathematics and the language of geometry. Over 2,000 years ago, Euclid laid the groundwork for all of modern mathematics as we know it today, and he asked the question that would inspire and frustrate mathematicians for millennia. The question that would lead us to discover the very nature of reality.